Hello, and welcome to Decision Revision with me, Will, and just me. I know I'm very lonely today. This is the first video I've ever done by myself, and I'm very scared. But moving on, decision is a bit of a weird aspect of mathematics. It involves basically thinking, which is always good. We're doing the Edexcel specification, but this does generally cover a lot of other specs, but you know, it's, mainly for Edexcel. Part 1. I'm going to be doing all the parts, hopefully, in this video. Part 1. Algorithms. The definition is it's a well-defined sequence of steps leading to the solution of a problem of a given type. You will be tested on whether you know the correct algorithm and whether you can follow steps accurately to solve a problem. When you're using an algorithm, it's probably best to use a trace table to follow with your working to keep trace of values, and then you might be asked as part of the question on certain values in the trace table. And yeah, I can't really say anything about that. You just have to kind of look at it. With flowcharts, if you're asked to draw a flowchart, which you might be, it's important that you always read or make a flowchart going down the page, going left to right. Start and stop should be in a bubble sort of thing. Yes or no should be in a triangle or a diamond more. And a do this or a command or something should be in a box if you're doing a flowchart. Right, the first set of algorithms you need to know is bin packing algorithms, and there are 3 of them. The first is full bin algorithm. You search, number 1, you search for combinations of values which exactly fit the bins. And number 2, for the remainder, place each item in the first available bin. Yeah, really, it's quite simple. Number 2, your second algorithm, you just take the items in the order listed and place each item in the first bin which has room for it. And the third algorithm is the first fit decreasing algorithm, which is you sort the list of values into decreasing order of size and then apply the first fit algorithm, where you take the items in the order listed, which are now in decreasing order of size, and place each item in the first bin which has room for it. Now each of these you will find as you do the questions will have, you know, some of them will use less bins if you like than others, and yeah, it depends, and some of them take longer than the other ones, which is never good. The other load of algorithms you need to know is sorting algorithms. There are 2 of these. Bubble sort, always bubbles. We love bubbles. Number 1, the first pass. This is where you compare the first and second numbers and swap them if they're in the wrong order. Then compare the second and third numbers and so on until the end of the list. You can write out each little swap and then as in a table that is 1 pass, or you can just, if you're clever, do 1 pass in your head and just write down each passes, but the question should specify. Number 2, for subsequent passes, repeat the above, leaving out the final number from the previous pass, which is now in the correct position if you're ordering it in that way. Number 3, terminating. Finish when the last pass has only 2 numbers or a complete pass has produced no swaps. So yeah, that's pretty self-explanatory. Yeah, basically. So yeah, even if there's no swaps and you keep going until you get to a number that you need to swap, so that in each pass there will be, the last number will be in the right place, and then so on. The second is a quick sort algorithm. Here you choose a middle number as the pivot, and selecting the middle number, there's an equation which you should know. I'm not going to read it out, but it's in the glossary if you have access to that, which you should do. You choose the middle number as the pivot, and for the remaining numbers, if the number is less than or equal to the pivot, place in a sublist before the pivot or in a sublist after. So I like to start with the first number in the list and compare it, leave it where it is if it's going, you know, on that list, or put it the first one after if it's going on the other list, and so on. That way you don't miss out any numbers. And then number 3 of that is quick sort sublists containing 2 or more numbers. So again, to choose the middle number in those as the pivot, and then for remaining numbers if they're less than or equal to the pivot, and so on. And then in each you should have the pivots, maybe circle the number. And so if you have the middle pivot of the first quick sort, keep that circled as you go down, because that is now in the right place. And then when everything's circled, or there's only, well, as it said, if there's 2 or there's 1 or less numbers, and you can stop, which is always lovely. I know it didn't make much sense, but what you can do. Searching is the final little algorithm-y based thing for just algorithms. And the only algorithm you need to know is binary searching. Number one, you find the middle item, M, of the search list using, and then here's the equation, which I said was in the glossary, M equals a half n plus 1 plus n plus 2, where n1 is the starting number and n2 is the ending number. And it's quite confusing, so I practiced that a bit to get your head around it, because it's very simple, but it's very confusing. Number two, if the target equals M, then the target has been found, and stop. If the target is less than M, then a new search list is the items below M, and if the target is more than M, then the new search list is the items above M. Then you repeat from step 1 until the target has been found, or the search list is empty, in which the target is not in the list. And that's very key for searching. Is that doing this way, is that the target might not be in the list, basically. On to graphs and networks now, the second part of, I can't remember, 6, 7, something like that. Graph theory, all you need to know is that the lines, if you like, that can be called a line, an edge, or an arc, and the points can be called a vertex, a node, or a point. If you've got one line going to the same, from the one vertex to the same vertex, that's a loop. And then if there's two lines between two vertices, then that's multiple edges, or there might be more than that. Right. Keywords. Keywords in graph theory. Graphs are isomorphic if they are the same but they look different. A graph is connected if you can travel from any vertex to any other. A graph with no loop or multiple edges is a simple graph. A subgraph has some vertices or edges of a graph, and a graph connecting all possible vertices is a complete graph. A graph with two distinct vertices set is a bipartite graph, and if every possible edge is connected, it is a complete bipartite graph. The degree of a vertex is the number of edges connecting to it. Total degrees equals 2 times the number of edges, and an adjacency matrix is a table representing the graph. That's a lot to get your head around. So again, little test cards would be lovely for them. Now, a network or a weighted graph has a number called a weight associated with each edge. A network can be represented by a distance matrix. For example, a train timetable is an example of a distance matrix. Sort of. A network satisfies the triangle inequality if for every set of 3 connected vertices A, B, and C, weight AB is less than or equal to weight AC plus weight BC. That is to check whether or not the network works, basically. Otherwise, it's lying to you, or you've done something wrong, or yeah, I think that's it. A digraph or a directed graph has at least one edge with an associated direction. A directed network is a weighted graph with directed edges. The corresponding distance matrices will be asymmetrical in this case, because you can only go one way along each line. It's a lot nicer, if that makes sense. Probably not. A path is a walk which does not pass through any vertex more than once, and a closed path is called a cycle or a circuit, and a connected graph with no cycles is a tree. So yes, that's basically where you have to pivot out of one point to get to places. That's how I like to think of it. A nice little pivoty thing. Transversing a graph now. If a graph is transversible, if it is, or Eulerian, cannot say that word, if it has a trail which is closed and which includes every edge once and once only. If you can only draw a graph like this by starting and ending at different points, it is semi-transversible or semi-Eulerian. I don't know, I haven't really been taught this, but I'm just going to say Eulerian and you'll remember it. A graph is transversible if all its vertices are of an even degree. A graph is semi-transversible if it has 2 odd vertices and they are the start and finish points. A graph with more than 2 odd vertices is not transversible. Yeah, until we get a bit later on, in which you have to basically make multiple edges, which is lovely. Minimum spanning trees now. A spanning tree or connector of a graph is a subgraph which is a tree containing every vertex of the graph. For n vertices, it requires n minus 1 edges. For a network, a spanning tree with the lowest total weight is a minimum spanning tree or minimum connector. To find this out, I believe there are two algorithms. The first one is Kruskal's algorithm. Number 1, choose any vertex to be the first connected set. Number 2, choose the edge of the minimum weight joining a connected vertex to an unconnected vertex, and add this to the edge. Add this edge to the spanning tree and the vertex to the connected set. Does that make sense? I hope it does. I've got no one to tell me that it doesn't, so it does. Then, if any unconnected vertices remain, go to step 2 and do it again. If at any stage there is a choice of edges, choose at random. So basically you mark the smallest, even if they're not connected. Really? That's all you got to do. Sounds all right. Prim's algorithm is separated into two parts depending on whether you have a graph or a distance matrix. If you have a distance matrix, I advise you use Prim's because Kruskal's is hard. For a graph, 1. Choose any vertex to be the first connected set. 2. Choose the edge of the minimum weight joining a connected vertex to an unconnected vertex. Add this edge to the spanning tree and the vertex to the connected set. Sorry, I'll read that again. Choose the edge of the minimum weight joining a connected vertex to an unconnected vertex and add this edge to the spanning tree and the vertex to the connected set. If any unconnected vertices remain, go to step 2 and do it again. For a distance matrix, 1. Select the first vertex, or they might give it to you if they're giving you a question. 2. Cross out the row for the chosen vertex. 3. Circle and number the column heading for the chosen vertex. 4. Find the minimum undeleted weight in the columns beneath the circled vertices, doesn't matter which column, and circle this value. The vertex for this row is the next chosen vertex. Number 5. Repeat steps 2, 3 and 4 until all of the vertices are chosen. If at any stage, again, if there is a choice of edges, choose at random. Now, the shortest path, which is, it takes ages, really. In a network, the shortest path between two vertices is one for which the total weight is minimum. And for this, you use Dijkstra's algorithm. You might call it Dijkstra's, or someone called it Dijkstra's the other day, but I call it Dijkstra's, so deal with it. Number 1, label the start vertex with a permanent label of 0. You'll see the labeling, how you should label it. It should give it to you, actually, if you've got it on a graph. To label the start vertex with a permanent label 0. Number 2, update all those vertices directly connected to V, the vertex permanently labeled 0, which do not have a permanent label. For each vertex, calculate L, the label of V, plus the label of Vx, or the weight of Vx. And then give X the temporary label L unless it already has a temporary label less than or equal to L. So basically you're adding the vertex you're on. So with your first, the first time you do it is 0 plus whatever the weight is on the arc to your vertexes. You write that in the temporary box if you like, and if that is, then once you've done all the vertexes in that round, if you like, then the lowest number becomes the permanent number. You label that with the order, and then you do it again. And then if the temporary number is, if you've got a new temporary number and it's lower than the temporary numbers it already has, cross it out and put in a new one. Now, you choose the vertex with the lowest temporary label at random if a tie, and permanently label it with this value. That's what I just said. If this is the destination vertex, then stop, otherwise go to step 2. Now, with Dijkstra's algorithm, if the vertex y is en route, then you find vertex x such that label y minus label x is the weight of xy. So that's when you're trying to find the shortest path, you work backwards by doing that. The vertex x is previous, then the vertex x is the previous vertex on the route, and so on. It can take a while, that's why I don't like it. The algorithms find the shortest path to all points from the starting point, so don't go doing it all again if they ask you for the distance from one place to the starting point, as long as it is the same starting point, otherwise you do have to do it all again. However, it doesn't work with negative numbers. That is a good negative thing if they ask you about that. Ah, see the pun there? And if you're watching this as a video, you can see a nice example of the sort of format you should leave it in. But if you're very good and sneaky, you will realise that the temporary numbers are actually wrong, because 6 is less than 7, so you wouldn't have put the 7 there, and 9, you wouldn't have put the 9 there, so that's just wrong, really. But it shows you the general idea of it, even though it's wrong. The route inspection problem can be stated as, for a given network, find the shortest route that travels at least once along every edge and returns to the starting point. If all vertices in the network are even, the network is transversable. The distance travelled is the sum of the weights. So imagine you have a park. This is a nice question. You had a park with loads of paths, and you want to inspect it for litter, and you only want to go along each path once. Yeah, how do you do it, really? And this is how. Identify, number 1, this is the algorithm for it. Number 1, identify the odd vertices. Number 2, list all possible pairings for the odd vertices. So if it's A, B, and C, you'd have A, B, A, C, B, C. That's all possible pairings. And for each pairing, or paring, as it says if you're watching the video, find the shortest routes between the paired vertices using Dijkstra's algorithm, or you can use it just looking at it if you're allowed to in the question. Find the sum of the weights involved. Number 4, choose the pairing with the smallest sum. By repeating the shortest route edges, the network becomes transversable. The total distance is the sum of the original weights plus the sum of the extra weights. On to matchings. The matching problem is really, for a bipartite graph, a matching M is a subset of the edges of the graph with the property that no two edges in M share a vertex. So M is a maximal matching if it contains the greatest possible number of edges. In a bipartite graph with equal numbers of vertices in each set, a matching M is a complete matching if M includes every vertex of the graph. To improve a matching, an alternating path joins an unmatched vertex in the left-hand set to an unmatched vertex in the right-hand set by edges which are alternately in and not in the set M of matched edges. Whoa. Take a minute, take it in, read it through. It's a revision, so yeah, basically you link one side that isn't matched to the other side that isn't matched. And that's really kind of it. When you change the status of the edges of an alternating path, those edges belonging to M are removed from M, and those edges not in M are added to M. That's what change the status is. And that is all relevant for the maximum matching algorithm. Yay! I think this is the last algorithm. Actually, no, there's another one. Never mind. Number 1, find a matching, the best you can easily find, or they might give you one. Number 2, search for an alternating path. If none exists, go to step 4. Number 3, form a new matching by changing the status, you now know what that is, of the edges in the alternating path, and go to step 2. Number 4, stop. The current maximum matching is maximal. Isn't that lovely? Now, linear programming is a bit of an odd thing, I think, to have in Decision, because it doesn't really go in with all the other things. It sort of does, but yeah. You have to produce what is called a linear programming formulation, which is quite confusing and quite hard to get your head around. But once you do get your head around it, it's quite enjoyable because it's loads of marks and it's quite simple if you know what you're doing. You basically, to produce a linear programming formulation, you identify quantities that you can vary, called the decision variables, or the control variables, so the ones that you can change. Then you identify the limitations of the values of the decision variables, and these are called the constraints. And then you identify the quantity to be optimized, called the objective function. For example, you're producing a whole load of raisins. I don't know why. Let's make it Haribos. I like Haribos. The decision variable will be the number of Haribos, because that is the thing that, you know, that you can control how many you produce. The constraints might be your ingredients, how much jello, I don't know, what makes Haribos, how much sugar, and that will be a constraint. And then the quantity to be optimized will be the amount of money you get from it, or the profit you get from it. So, solving problems graphically, you basically plot it on a graph using the, I don't know if there's an algorithm. I don't have one. There might be. Have a look. The feasible region is the set of xy values which satisfy all the constraints, and this is basically the unshaded region of the graph. So you'll have by having your decision variables and constraints and objective function, you make equations or inequalities, I think they're called, and you plot that on the graph, shading out bits, and you're left with a little region. And the unshaded region of the graph is the feasible region, where the values of the graph are satisfied by all the constraints and everything, really. The objective line is a line joining all the points x, y for which the objective function takes a specific value. So if you want the profit to equal something in particular, then there will be a line for which that will x and y will, make that. And yeah, basically, I think that's quite simple. If it isn't, then look at it in your own time, because we're nearly finished. Now we're on to critical path analysis, which everybody loves. Critical path analysis. It's another slightly strange one. Modelling the problem. Features of a precedence table or a dependence table. You have a list of activities, the details of which activities depend on which, and how long each will take, known as the duration. The features of an activity network. Each activity is represented by an arc. The weight is the duration, and each node represents the event of completing one or more activities, with one start, the source, 0, and one finishing or sink node. You name an activity by its starting node, the tail event, and the finishing node, the head event. To avoid having the same tail and head event, you may use a dummy activity shown by a dotted line with a 0 duration. So, for example, for a line, or which is an activity, or an arc, if the vertex before it is 3 and the vertex after it is 2, that makes sense. But it wouldn't be that; it would be 2 and then 3 because in order. Then you would have E2, 3, and that's the tail event and the head event for it, which is good. They can't be the same, which is why you would have a dummy activity, because you can't have the same identity, if you like. Finding the critical path. EI is the earliest event time and LI is the latest event time, and these are important for the question. To find EI, you make a forward pass. For event J with several incoming activities, IJ, EJ is the maximum of EI plus the duration of IJ. The EI for the sync node is the maximum project duration. To find LI, you make a backward pass. For the event LI with several outgoing activities, IJ, LI is the minimum of LJ minus the duration of IJ. Now, the thing about maths sometimes is when you read it out, it sounds just horrible and you have no idea what's going on. So I just advise you to look at an example for any of these that you don't understand, and that'll do you. To find the critical path, which we're already doing, you might be asked to find the slack or SI for an event, which is just the latest you can do the event minus the earliest time that you can do it, if you like, which finds the gap, so the amount of time you have to play with, if you like. If an event is critical, then EI will equal LI. So there will be no slack, which means it's critical because you have to do it at the time set and there's no sort of playing around. Time available for the activity is Li minus EI, or the slack. The total float for an activity is Li minus EI minus the duration of IJ. So that's how much an activity, how much you can vary when it starts and stops. If float equals 0, then the activity, again, is critical. See how they all relate? Isn't that clever? And here is, I promised, the last algorithm, the critical path algorithm. 1. Perform a forward pass recording the earliest event times EI. 2. Perform a backward pass recording the latest event times LI. 3. Calculate the total float for each activity. Lots of people forget that in exam questions. And number 4. Activities for which the float equals 0 form the critical path. And then you'll probably be asked to write out the critical path. Or just write it out, because it's always good, because that's what we're trying to find. That's the point of this topic. That's what I'm talking to. Gantt charts, or I call them Gantt, because I sort of heard them wrong when I first saw them, and or I read them wrong, and it's stuck. So I call them Gantt, even though they're Gantt. Don't know why. But there we are. For activity ij, the earliest finish time will be ei plus the duration of ij, and the latest start time will be li minus the duration of ij. Ready? I think that's quite simple. Always leave a gap between the bars vertically when you're doing a Gantt or a Gantt chart, and place the critical path side by side as the first row. It's a nice little thing to do. Again, if you don't know what I'm talking about, have a look. Scheduling is the very, very, very last thing in decision. This is the longest video we've ever made, longer than the history ones, and we all know how long they go on. Scheduling, the scheduling procedure, the project clock starts at 0. If there is a free work, this is, oh wait, no, this is another algorithm. I'm very sorry, this is the last algorithm. Number 1, if there is a free worker and an activity which can be started, assign the worker to the activity. If there is a choice of activities, choose the most critical one, and repeat until no worker is free or no activity is available. Number 2, if all activities have been assigned, then stop. Otherwise, advance the project clock until there is a free worker and an activity that can be started and go to step 1. When scheduling, you must assume that each activity needs one worker. No worker can stand idle if there is an available activity, and once a worker starts an activity, it will be continued until it's complete. The most critical activity is the one with the smallest, latest starting time. Yeah, I don't think I should waste your time explaining that. I think it's quite explanatory. And again, they're all graphs. Thank you for listening. I know it's been hard because it's very hard to talk about things that you can't see. Or, you know, I haven't given any examples, but yeah, this is revision. This should be last minute. So good luck in your decision exam. It's all very good. It's all very fun. It's all very lovely. And yeah, that's all. That is the whole topic in 26 minutes. Thank you very much for listening. Bye.